For decades, the Sun was studied from a safe distance. Telescopes watched its surface. Satellites orbited far beyond its reach. Scientists measured light, radiation, and streams of particles that drifted outward through space. The Sun was close enough to see every day, yet distant enough to remain untouched. It dominates our sky. It shapes our climate. It controls the motion of every planet in the solar system. And still, there was a boundary no spacecraft had ever crossed. The outer atmosphere of the Sun, called the corona, stretches millions of kilometers into space. It glows during a total solar eclipse as a faint white halo around the darkened Sun. From Earth, it looks delicate. From space, it is a region of violent heat and motion. The corona can reach temperatures above 1 million degrees Celsius. That number alone carries weight. But what makes it even stranger is this. The visible surface of the Sun, the photosphere, is only about 5,500 degrees Celsius. Higher above the surface, the temperature rises instead of falling. Heat grows stronger as you move outward. For generations, this created a quiet puzzle. Energy usually spreads outward and cools. Campfires fade as you step back. Warm air becomes cooler with distance. Yet in the Sun's outer layers, the air becomes hotter. Scientists built models. They studied magnetic fields. They measured waves in plasma. They searched for signs of tiny bursts of energy that could explain the heating. But all of this was done from afar. It is one thing to watch waves on the ocean from the shore. It is another to float within them. In 2018, a spacecraft began a journey that would change that distance. It was called the Parker Solar Probe. Launched on August 12, 2018, aboard a Delta IV Heavy rocket, it began spiraling inward toward the Sun. It did not travel straight in. Instead, it used repeated flybys of Venus, allowing gravity to bend and shrink its orbit over time. With each pass, it moved closer. Closer than Mercury. Closer than any spacecraft before it. Its goal was direct contact with the Sun's outer atmosphere. On April 28, 2021, during its 8th close approach, the spacecraft crossed a boundary known as the Alfvén critical surface. This boundary marks a shift in control. Outside it, the solar wind flows freely outward into space. Inside it, the Sun's magnetic forces still guide and shape the motion of particles. When the Parker Solar Probe crossed that boundary, it entered the corona itself. NASA described the moment in simple words. Humanity had touched the Sun. The spacecraft did not land. It did not skim the visible surface. It entered the atmosphere that surrounds it. At its closest approach, Parker traveled roughly 6.2 million kilometers from the Sun's center. It moved at speeds exceeding 600,000 kilometers per hour. At that velocity, it became the fastest human-made object in history. The heat it faced was intense. Its heat shield, nearly 2.4 meters wide and about 11 centimeters thick, endured temperatures around 1,370 degrees Celsius. Behind that shield, the spacecraft's instruments remained near room temperature. Protected by shadow, the probe began measuring the Sun directly. It recorded magnetic fields. It sampled charged particles. It detected waves moving through hot plasma. For the first time, data came from inside the corona rather than from the edge of it. The sun was no longer only observed. It was entered. A small machine, protected by a thin shield of carbon and careful engineering, crossed a boundary that once seemed unreachable. And in doing so, it opened a new way of understanding the star that has shaped every day of human history. We had touched the sun. Before any spacecraft approached the sun, there was a question that refused to settle. It was a quiet question at first. Then it grew into one of the longest-running puzzles in solar physics. Why is the sun's outer atmosphere hotter than its surface? The visible surface of the sun, the photosphere, sits at about 5,500 degrees Celsius. That number already represents extraordinary heat. It is hot enough to melt rock, hot enough to shape the weather of an entire planet from 150 million kilometers away. Yet above that surface lies the corona. The corona can reach temperatures of 1 to 2 million degrees Celsius. In some regions, it grows even hotter. The air grows more energetic as it moves away from the furnace below. This became known as the coronal heating problem. It is not a small temperature difference. It is not a gentle rise. It is an increase of hundreds of times. For decades, scientists tried to understand how this could happen. They knew the sun is made of plasma. Plasma is a state of matter where atoms are stripped of electrons. It behaves differently than solid, liquid, or gas. It responds strongly to magnetic fields. The sun's interior moves constantly. Hot plasma rises from deep within. Cooler plasma sinks. This churning motion creates magnetic fields. Those magnetic fields twist, stretch, and loop above the surface. They form arches and strands that reach into the corona. They store energy in invisible lines of force. One idea was that waves carry energy upward. These waves are called Alfvén waves. They travel along magnetic field lines. They move through plasma like ripples traveling along a stretched rope. If enough of these waves rise into the corona and release their energy, they could heat the surrounding plasma. Another idea involved magnetic reconnection. Magnetic field lines can snap and reconnect. When they do, they release energy suddenly. This process powers solar flares. It may also happen on smaller scales thousands of times each second. Some researchers proposed tiny bursts called nanoflares. Each burst would be small, but together millions of them could warm the corona. There was also the idea of turbulence. Large motions in plasma can break into smaller and smaller motions. Energy cascades downward to tiny scales. At those small scales, it turns into heat. Each theory had supporting evidence. Each theory also left gaps. The difficulty was distance. Most spacecraft remained far outside the region where these processes begin. They measured the solar wind after it had already accelerated. They detected magnetic fluctuations after they had traveled outward. It was like studying wind patterns from the edge of a storm instead of inside it. There was also another connected mystery: the solar wind itself. The sun constantly releases a stream of charged particles. This stream flows outward through the solar system. It fills space with a thin, invisible breeze. The solar wind travels at hundreds of kilometers per second. Some streams move faster than others. Some carry more energy. Scientists wanted to understand how the solar wind accelerates. Where does it gain its speed? How does it escape the sun's gravity? How do magnetic structures near the surface influence the wind far beyond? These questions mattered for Earth. Solar wind shapes space weather. It interacts with Earth's magnetic field. It can disrupt satellites. It can interfere with power grids. It can produce brilliant auroras in polar skies. Large solar storms have affected telegraph systems in the past. Modern technology is more sensitive. Predicting space weather requires understanding the sun at its source. For decades, researchers collected pieces of the puzzle. They watched from orbit. They simulated plasma in supercomputers. They analyzed signals carried millions of kilometers across space. But a key region remained unmeasured. The region where the solar wind is born. The region where magnetic energy becomes motion. The region where heat rises to impossible levels. To solve the coronal heating problem and the solar wind acceleration problem, measurements had to be taken inside the environment itself. That was the quiet motivation behind the Parker Solar Probe. Its mission was not built around spectacle. It was built around a stubborn scientific question that had lingered for more than half a century. A question about heat rising upward. A question about energy moving through invisible lines of force. A question that could only be answered by entering the atmosphere of a star. There is no solid wall around the sun. There is no visible line in space that marks where it ends. Yet there is a boundary. It is a boundary made of motion and magnetism. For decades, scientists described it using a term that sounds technical, but carries a simple meaning. The Alfvén critical surface. To understand this boundary, it helps to begin with plasma. The sun is made of plasma. Plasma is gas-heated so intensely that electrons are stripped from atoms. What remains is a mix of positively charged ions and free electrons. This mixture conducts electricity. It responds strongly to magnetic fields. Inside the sun's atmosphere, magnetic fields shape how plasma moves. Particles spiral along magnetic field lines. Energy travels through waves along those lines. Magnetism dominates the motion. But as plasma flows outward from the sun, something changes. The solar wind accelerates. It gains speed. As it travels farther away, it stretches outward into the solar system. At some point, the outward motion becomes stronger than the magnetic grip holding it close. That transition marks the Alfvén critical surface. The name comes from Hannes Alfvén, a physicist who helped develop the theory of magnetohydrodynamics. Magnetohydrodynamics studies how magnetic fields interact with electrically conducting fluids like plasma. The Alfvén surface is defined by speed. Specifically, it is the distance from the sun where the speed of the solar wind becomes equal to the speed of Alfvén waves. Alfvén waves are ripples that travel along magnetic field lines in plasma. They carry energy outward. They move at a specific speed determined by the strength of the magnetic field and the density of the plasma. Inside the Alfvén surface, magnetic waves can travel both outward and back toward the sun. The sun's magnetic field still controls the plasma in this region. Outside the surface, the solar wind flows faster than those waves can travel backward. At that point, the plasma effectively escapes. The sun's magnetic control weakens. The wind becomes free-flowing. In simple terms, the Alfvén surface marks the outer edge of the sun's atmosphere. Inside it, the sun still feels connected to the plasma. Outside it, the wind carries energy away without returning. For years, scientists estimated that this surface might lie somewhere between about 10 and 20 solar radii from the Sun's center. A solar radius is about 696,000 kilometers. 10 solar radii would place the boundary nearly 7 million kilometers from the center. These estimates came from indirect observations. Spacecraft like Helios and others measured solar wind properties farther out. Models were built to trace the behavior inward, but no spacecraft had directly sampled the region where the transition occurs. Until Parker. During its 8th close approach on April 28, 2021, the Parker Solar Probe crossed into this magnetically dominated region. The spacecraft detected a shift in magnetic field behavior. It recorded changes in plasma density and wave patterns. The data showed that it had entered a region where the solar wind had not yet fully escaped. In fact, Parker moved in and out of the Alfvén surface multiple times during that encounter. The boundary was not smooth. It appeared uneven, shaped by magnetic structures extending outward from the Sun. Scientists described it as having spikes and valleys. This revealed something important. The Sun's atmosphere is not a perfect sphere of calm plasma. It is textured. It shifts with solar activity. Its boundaries move. Crossing the Alfvén surface was described by NASA as touching the Sun. The phrase is symbolic. The spacecraft did not reach the photosphere. It entered the outer atmosphere where the Sun's magnetic influence remains dominant. This marked the first time a human-made object directly sampled the corona from within. The boundary was once theoretical. It was defined in equations and simulations. Now it had been measured in place. The data from that crossing provided insight into how energy and motion are transferred outward. It showed where the solar wind begins to break free. It offered a clearer picture of how magnetism shapes the Sun's extended atmosphere. A line that once existed only in theory had become a place. And a small spacecraft, shielded by carbon and guided by careful engineering, had crossed it. Before the Parker Solar Probe could cross any magnetic boundary, it had to survive the heat. Approaching the Sun is not simply a matter of distance. It is a matter of energy. At its closest approach, Parker travels roughly 6.2 million kilometers from the Sun's center. That distance is only about 9.9 solar radii. For comparison, Mercury orbits at an average distance of about 58 million kilometers. The sunlight at Parker's closest pass is nearly 500 times more intense than the sunlight Earth receives. That intensity carries enormous thermal energy. Without protection, the spacecraft would overheat almost instantly. The key to survival is a structure called the thermal protection system. The heat shield is about 2.4 meters in diameter. It is roughly 11.4 centimeters thick. It sits at the front of the spacecraft like a round, flat disc. The shield is built from carbon composite materials. 2 carbon plates enclose a lightweight carbon foam core. The foam is about 97% air by volume. Air is a poor conductor of heat, which helps reduce the flow of energy through the shield. The sun-facing surface is coated in a white ceramic layer. This coating reflects as much solar radiation as possible. During closest approach, the front of the shield can reach temperatures near 1,370 degrees Celsius. That is hot enough to melt many metals. Yet behind the shield, the spacecraft remains near room temperature. The difference between the front and back is dramatic. The shield works by blocking and absorbing energy. It also creates shade. Most of the spacecraft hides entirely within the shadow of the shield. The probe must remain precisely aligned so that the shield faces the sun at all times during perihelion. If it drifts even slightly out of alignment, parts of the spacecraft could be exposed to direct sunlight. To prevent this, Parker is equipped with an autonomous guidance system. There is a delay in communication between Earth and the spacecraft. Radio signals take about 8 minutes to travel one way near the sun. During close passes, the probe must protect itself without waiting for instructions. Sensors monitor sunlight intensity and orientation. If the spacecraft begins to rotate away from its protective position, onboard systems automatically correct its attitude. It is a form of self-preservation built into the flight software. Heat protection involves more than just the shield. The spacecraft also carries a liquid cooling system. Water flows through a closed-loop system connected to radiators. This system absorbs excess heat from certain components and releases it into space. Even the solar panels must be managed carefully. At large distances from the sun, the panels extend outward to gather energy. As the spacecraft moves inward, the panels retract partially into the shield's shadow. Only a small portion remains exposed to sunlight during closest approach. These exposed sections are water-cooled to prevent overheating. The coolant itself must be protected. Between close encounters, when the spacecraft travels farther from the sun, temperatures drop sharply. The coolant tank is equipped with heaters to prevent freezing. The mission required careful balance. Too much protection would add mass. More mass would require more energy to launch and maneuver. Too little protection would risk failure. The shield, cooling system, and retractable panels work together as a unified system. The design allows the instruments behind the shield to function properly. Those instruments measure electric and magnetic fields. They count charged particles. They detect waves moving through plasma. None of that would be possible without stable internal temperatures. At its fastest, Parker moves at speeds approaching 190 kilometers per second. That is roughly 687,000 kilometers per hour. At that speed, it becomes the fastest human-made object ever built. Yet speed alone does not provide safety. It is the careful engineering of thermal control and orientation that allows the spacecraft to survive. The sun radiates energy in all directions. The Parker Solar Probe meets that energy with a circle of carbon and silence. A thin shield stands between intense heat and delicate electronics. Behind that shield, instruments wait patiently. They measure a region of space that was once unreachable. A few centimeters of engineered material separate fire from function. And within that narrow band of protection, the spacecraft continues its steady path around a star. Behind the heat shield, hidden in shadow, the Parker Solar Probe carries its senses. It does not see the sun the way a camera on Earth does. It does not rely only on light. It measures invisible forces. It measures charged particles. It measures waves moving through hot plasma. Each instrument on board was designed to answer a specific part of the long-standing questions about the corona and the solar wind. Together, they act like a set of senses placed directly inside the sun's outer atmosphere. One set of instruments measures electric and magnetic fields. This system is simply called fields. It listens to the invisible structure of space around the spacecraft. It detects how magnetic fields bend and shift. It measures how those fields change over time. It also senses waves traveling through plasma. Magnetic fields carry energy in the sun's atmosphere. They twist, they stretch, they store tension like coiled springs. When those fields move, small ripples travel along them. By measuring tiny fluctuations, the field instruments can detect Alfvén waves. They can track turbulence. They can observe sudden reversals in magnetic direction. These sharp bends became known as switchbacks. A switchback is a brief flip in the magnetic field. Instead of flowing smoothly outward, the field suddenly bends back toward the sun before straightening again. Before Parker flew inward, switchbacks had been detected much farther from the sun. Their origin remained uncertain. By measuring them closer to the source, scientists began tracing where they form and how they evolve. Another set of instruments measures the particles themselves. This system studies the solar wind by counting electrons, protons, and helium nuclei. It measures how many particles pass by. It measures their speed. It measures their temperature. Some of its sensors face directly toward the sun. These are small cups that sit slightly beyond the edge of the shield's shadow. They sample particles streaming outward at high speed. Other sensors look in different directions, measuring particles arriving from multiple angles. Together, these measurements reveal how the solar wind accelerates. They show how energy stored in magnetic fields turns into motion. A third system measures even more energetic particles. This instrument studies particles that carry far greater energy than the ordinary solar wind. Some of these particles are linked to solar flares. Others are connected to shock waves from coronal mass ejections. Their energies range from thousands of electron volts up to tens of millions of electron volts. By detecting these particles close to the sun, scientists can determine where they are accelerated. This improves understanding of radiation hazards in deep space. It also helps explain how violent solar events develop. Finally, there is a camera. Unlike the other instruments, this one captures visible light. It images the corona and the inner solar wind. It sees sunlight scattered by free electrons in plasma. Through that scattered light, it reveals streamers, jets, and massive clouds of material moving outward. These images provide context. While the field and particle instruments measure local conditions directly around the spacecraft, the camera shows the larger structures surrounding it. When the probe passes through turbulence or crosses magnetic boundaries, the images sometimes reveal visible features linked to those changes. Together, the instruments create layered understanding. One system listens to invisible magnetic forces. Another measures the particles responding to those forces. Another tracks the highest energy particles born from explosive events. And the camera shows the wider environment where it all unfolds. The spacecraft does not simply travel through space. It listens to waves. It feels the flow of charged particles. It watches solar storms from within. When data from all these systems are combined, patterns emerge. Magnetic shifts can be compared with particle speeds. Energetic bursts can be matched with visible structures. The behavior of plasma becomes clearer. Inside the narrow shadow of its shield, the probe quietly gathers information. It records the behavior of matter at temperatures once unreachable. It measures forces that shape the entire solar system. And through these instruments, the Sun's outer atmosphere becomes something we can sense directly, rather than only imagine from afar. If we are going to understand what the Parker Solar Probe entered, it helps to begin deep inside the Sun itself. Imagine a quiet tour inward. The Sun is not a solid ball of fire. It is layered. It is structured. It is motion stacked inside motion. At the very center lies the core. The core reaches temperatures of about 15 million Kelvin. That is where nuclear fusion takes place. Hydrogen atoms combine to form helium. In that process, small amounts of mass turn into energy. This energy is the source of all sunlight. Every second, the Sun converts about 600 million tons of hydrogen into helium. A small fraction of that mass becomes pure energy. That energy begins a slow journey outward. Above the core sits the radiative zone. In this region, energy moves primarily through radiation. Photons scatter and are absorbed repeatedly by particles in the dense plasma. Each photon may travel only a short distance before changing direction. This process is slow. A single packet of energy can take hundreds of thousands of years to move from the core through the radiative zone. Temperatures in this region remain extremely high. They range from several million Kelvin near the core down to about 2 million Kelvin near the outer boundary. Even though it is called the radiative zone, it is not calm or empty. It is dense plasma under intense pressure. Above the radiative zone lies the convective zone. Here, energy no longer moves mainly through radiation. Instead, it moves through convection. Hot plasma rises toward the surface. As it rises, it cools slightly. Cooler plasma then sinks back downward. This cycle repeats continuously. It is similar to water slowly boiling in a pot. Large cells of rising and sinking plasma fill this region. The convective zone extends from about 70% of the Sun's radius outward to the visible surface. Temperatures here drop from roughly 2 million Kelvin down to around 5,500 Kelvin at the surface. This constant rising and falling motion has consequences. Plasma is electrically charged. As it moves, it drags magnetic field lines with it. Over time, this motion twists and stretches magnetic fields. Field lines become tangled. They loop outward from the surface. They store energy like stretched rubber bands. These magnetic structures eventually reach into the Sun's atmosphere. Sunspots form where magnetic fields concentrate and suppress convection. Solar flares occur when twisted magnetic fields release energy suddenly. All of this begins deep below the surface. The core provides energy through fusion. The radiative zone carries that energy outward slowly. The convective zone stirs the outer layers, shaping magnetism. By the time energy reaches the surface, it has traveled a long internal path. The Sun is not a static sphere glowing quietly. It is layered motion. Fusion drives radiation. Radiation feeds convection. Convection sculpts magnetism. And magnetism reaches upward into the corona, the very region the Parker Solar Probe entered. Understanding these layers makes the surface feel thinner. The visible light we see is only the final expression of energy that began in a 15 million degree core. Beneath that light lies depth. Beneath that glow lies motion that has been unfolding for billions of years. The Sun is not simply hot, it is structured heat. layered energy rising slowly from its center and shaping the light that reaches us each day. The sun is motion, layered into light. If you were standing in space far enough away to look safely at the sun, your eyes would be drawn to its bright surface. That glowing disk is called the photosphere. It is the layer that gives us most of the visible sunlight we receive on Earth. It feels thick and solid when we look at it. In reality, it is thin. The photosphere is only about 400 kilometers thick, compared to the sun's full radius of about 696,000 kilometers. That is extremely shallow. It is like a thin skin stretched over a deep furnace. The temperature of the photosphere ranges from about 4,000 Kelvin in cooler regions to roughly 6,500 Kelvin in hotter areas. That translates to about 6,700 to 11,000 degrees Fahrenheit. These temperatures produce the visible light that fills our sky, the light that warms your skin, the light that allows plants to grow, the light that defines day and night. The photosphere is where the sun becomes visible to human eyes. Below it, the plasma is opaque. Photons scatter too frequently to escape. At the photosphere, the plasma becomes thin enough for light to travel outward freely. This is why we call it the surface, even though it is not solid. When viewed through powerful telescopes, the photosphere does not appear smooth. It has a textured, grainy pattern. This pattern is called granulation. Each bright patch, or granule, is about 1,000 kilometers across. Granules form because of convection below. Hot plasma rises from the convective zone beneath. As it reaches the photosphere, it cools slightly and spreads outward. Then it sinks again at the darker edges between granules. This creates a constantly shifting mosaic of rising and falling plasma. Each granule lasts only about 5 to 10 minutes before dissolving and reforming. The entire surface is alive with motion. Sunspots also appear on the photosphere. They look darker because they are cooler than the surrounding areas. Typical sunspot temperatures are around 3,000 to 4,500 Kelvin. They form where strong magnetic fields rise through the surface and suppress convection. Without rising hot plasma, those regions cool slightly. Even the coolest sunspots are still extremely hot by Earth standards. The photosphere is also the starting point for many solar phenomena. Solar flares erupt from regions of intense magnetic activity. Prominences rise above the surface, shaped by magnetic loops. Coronal mass ejections begin near these active areas. Everything visible on the sun begins here. The photosphere marks the boundary between the deep interior and the outer atmosphere. It is where light escapes after traveling for thousands or even millions of years from the core. The energy that began as fusion in the core finally emerges as visible sunlight. Yet for all its brightness, the photosphere is only a thin layer. Above it, temperatures will rise again in unexpected ways. Above it, magnetism becomes even more dominant. Above it, the environment shifts from what looks familiar to something far more extreme. When we speak about touching the sun, we are not speaking about this glowing surface. The Parker Solar Probe never skimmed the photosphere. Instead, it entered the layers above. But to understand that outer atmosphere, it helps to see the photosphere clearly. It is the thin edge where light leaves the sun. It is the final step of a journey that began at 15 million Kelvin in the core. It is textured by convection and shaped by magnetism. And though it shines with intense brightness, it is only a surface resting over vast depth. A thin skin stretched over a furnace that has burned for billions of years. If we continue our slow climb upward from the photosphere, the air does not simply thin and cool. Instead, something unusual begins to happen. Just above the visible surface lies a layer called the chromosphere. The chromosphere extends from roughly 250 kilometers above the photosphere up to around 2,000 kilometers. Compared to the Sun's total size, this is still a very thin region. Yet within this thin band, the behavior of temperature begins to shift. Near the bottom of the chromosphere, temperatures are close to 4,000 Kelvin. As you move upward, temperatures rise. By the upper chromosphere, temperatures reach around 8,000 Kelvin. This rise is not smooth. The chromosphere is dynamic. It contains spicules, which are narrow jets of plasma that shoot upward at speeds of about 20 to 100 kilometers per second. Some spicules rise thousands of kilometers before falling back. Others may contribute material directly into the corona. The chromosphere is also shaped strongly by magnetic fields. Where magnetic field lines concentrate, plasma follows their paths. In these regions, loops and arches become visible during solar eclipses or through specialized telescopes. The chromosphere glows faintly in a reddish color when viewed through hydrogen alpha filters. That red glow is where the name comes from. Chromo means color. But the chromosphere is only the beginning of the temperature puzzle. Above it lies one of the thinnest yet most dramatic layers of the Sun, the transition region. The transition region is incredibly thin. It is estimated to be only about 100 kilometers thick in some places. That is thinner than the chromosphere below it. And yet, across this narrow distance, the temperature changes rapidly. At the base of the transition region, temperatures are around 8,000 Kelvin. Within a short span upward, temperatures leap to hundreds of thousands of Kelvin. In some regions, they approach 500,000 Kelvin or more. It is one of the sharpest temperature gradients in the solar atmosphere. Imagine climbing a mountain where the air suddenly becomes hotter with each step upward. The transition region marks the shift from the relatively cooler lower atmosphere to the million-degree corona above. The reason for this rapid increase is tied to magnetism and plasma physics. Energy transported through magnetic waves and reconnection events deposits heat into the upper atmosphere. Particles begin to move more freely. The density drops. The plasma becomes more influenced by magnetic forces than by collisions between particles. In this region, the Sun's atmosphere changes character. Below the transition region, plasma behavior is more tightly coupled to the dense layers beneath. Above it, the corona begins. The transition region is difficult to study from afar. It emits light in ultraviolet wavelengths rather than visible light. Space-based observatories are required to observe it clearly. Even then, its thinness makes it challenging to measure directly. The Parker Solar Probe does not linger in the chromosphere or transition region. It does not skim the photosphere either. But understanding these layers is essential. They form the gateway to the corona. They are the steps between the visible surface and the million-degree atmosphere beyond. The steady rise in temperature through the chromosphere already begins to defy simple expectations. Then, in the transition region, the increase becomes dramatic. The air grows thinner. The particles move faster. Magnetic fields play a greater role. By the time we reach the corona, the rules feel different. Heat has risen where it should have faded. The thin outer layers of the sun are not passive. They are shaped by energy traveling upward from below. They are structured by magnetic lines reaching outward. And as we step upward through these layers, the familiar glow of the photosphere gives way to a region where light is faint, but heat is extreme. The chromosphere rises gently. The transition region leaps sharply. And above them waits the million-degree mystery that drew the Parker Solar Probe inward in the first place. Above the transition region, the sun opens into something that looks almost weightless. During a total solar eclipse, when the bright surface is hidden, a pale halo becomes visible around the dark disk. That halo is the corona. It stretches millions of kilometers outward into space. In photographs taken from Earth or from orbit, the corona appears soft and delicate. Long streamers extend outward like glowing threads. Loops of light arc away from the surface. Jets of plasma sometimes burst into space. But the appearance is deceptive. The corona is not cool. It is not faint because it lacks energy. It is faint because it is thin. The density of particles in the corona is extremely low compared to the layers below. Yet despite this low density, its temperature is astonishing. Typical coronal temperatures near its base range from 1 to 2 million Kelvin. In certain active regions, temperatures can rise even higher. Some measurements show temperatures exceeding 2 million degrees Fahrenheit, while the photosphere below remains around 10,000 degrees Fahrenheit. This contrast forms the heart of the coronal heating problem. If the sun's energy is generated in its core and flows outward, one might expect the outer layers to cool steadily with distance. Instead, after cooling to about 4,000 Kelvin in parts of the lower atmosphere, the temperature climbs sharply again. The outer atmosphere becomes hundreds of times hotter than the visible surface. This is not a small variation. It is not a rounding difference. It is a dramatic reversal. The corona is also the birthplace of the solar wind. The solar wind is a continuous stream of charged particles flowing outward from the sun. These particles include electrons, protons, and helium nuclei. Near the corona, the solar wind begins to accelerate. Particles gain speed as they move outward. By the time they reach Earth's orbit, typical solar wind speeds range from about 300 to 800 kilometers per second. The corona is shaped by magnetic fields. Magnetic loops rise from the photosphere and extend high into the corona. Some loops close back down onto the surface. Others open outward into space. Where field lines open, particles can escape more easily. These open regions often correspond to coronal holes. Coronal holes appear darker in ultraviolet images. They are regions where the magnetic field lines extend outward into space rather than looping back. Vast solar wind streams often emerge from these areas. The corona is not static. It pulses with activity. Solar flares erupt when magnetic fields release stored energy suddenly. Coronal mass ejections send billions of tons of plasma into space. Waves ripple through the hot plasma. Turbulence stirs the atmosphere. Despite decades of observation, the full explanation for the corona's extreme heat remains incomplete. Several heating mechanisms are still under study. Alfvén waves may carry energy upward along magnetic field lines. Magnetic reconnection may release energy in countless small bursts. Turbulence may transfer energy from large motions to smaller scales where it becomes heat. Each of these ideas has support. None has fully closed the case. The corona is also where the Parker Solar Probe entered. When the spacecraft crossed the Alfvén critical surface, it moved into a region where magnetic forces still shaped the plasma's motion. It sampled particles directly in this million-degree environment. It measured magnetic fluctuations at their source. It recorded data where theory had once stood alone. The corona's heat is not felt the way heat is felt on Earth. Because the density is so low, an object passing through the corona does not experience the same type of heating as it would in dense air. The danger comes from intense radiation and high-energy particles, not from thick, scorching gas. This distinction made the mission possible. The corona is a paradox. It is thin, yet extremely hot. It is faint, yet filled with energy. It surrounds the sun like a glowing veil, stretching outward into the solar system. For centuries, it was visible only during rare eclipses. Now, it is measured from within. Its temperature rise still challenges simple intuition. Its magnetic structures still twist and reshape. Its energy still flows outward into space, carrying influence far beyond the sun itself. The corona hangs above the surface like a warm fog rising from cooler ground. It glows softly in photographs. Yet inside that glow lies one of the most enduring mysteries in solar physics. A mystery that a small spacecraft now moves quietly through, collecting answers one orbit at a time. If you could scoop a handful of air from Earth, it would feel familiar. It would be made of neutral atoms and molecules. It would follow the ordinary rules of gas. The sun is different. The sun is made of plasma. Plasma is often called the fourth state of matter. It forms when gas becomes so hot that electrons are stripped away from atoms. What remains is a mixture of positively charged ions and free electrons. Because the particles are charged, they respond strongly to magnetic fields. This changes everything. On Earth, wind moves because of pressure differences and temperature changes. In the sun's atmosphere, motion is shaped not only by heat and pressure, but by magnetism. Magnetic fields thread through solar plasma. In many cases, the magnetic field and the plasma move together. Scientists describe this by saying the magnetic field is frozen into the plasma. In practical terms, this means the plasma and magnetic field lines travel as a linked system. If plasma flows upward, it drags magnetic field lines with it. If field lines twist, the plasma follows their shape. This is the foundation of solar magnetism. Deep below the surface, in the convective zone, hot plasma rises and cooler plasma sinks. As this motion unfolds, it stretches and tangles magnetic field lines. Over time, the sun's rotation also plays a role. The equator rotates faster than the poles. This difference twists magnetic fields even more. Eventually, loops of magnetism rise through the photosphere. These loops can form sunspots at their bases. They can store energy as they become twisted and strained. When that tension is released, solar flares and coronal mass ejections can occur. Above the surface in the chromosphere and corona, the role of magnetism becomes even stronger. The plasma density drops. Particles collide less frequently. Magnetic forces dominate motion. In the corona, the movement of plasma is often guided along magnetic field lines. Particles spiral around those lines as they travel. Energy moves through waves along them. The corona becomes a landscape shaped by invisible rails. These rails determine where plasma flows freely and where it is trapped in loops. They determine where energy accumulates and where it escapes. When the Parker Solar Probe entered the corona, it moved into a region where these magnetic forces controlled the behavior of matter. The spacecraft's instruments detected fluctuations in magnetic fields. They measured waves traveling along field lines. They observed how charged particles responded to those forces. Understanding plasma and magnetism is key to understanding the coronal heating problem. If magnetic fields store energy, that energy must be released somehow. If waves carry energy upward, they must deposit it somewhere. In plasma, small-scale processes can have large-scale consequences. Turbulence can transfer energy from large motions down to tiny scales. At those tiny scales, energy can become heat. Magnetic reconnection can snap and rejoin field lines. When that happens, stored magnetic energy converts into motion, light, and heat. Because plasma conducts electricity, it also supports electric currents. These currents flow along magnetic field lines. Where currents concentrate, energy density can increase. All of this occurs in a medium that is neither solid nor ordinary gas. Plasma responds to forces differently. It supports waves that do not exist in neutral air. It allows magnetic fields to shape motion across vast distances. When scientists study the sun, they are studying plasma physics on a grand scale. The sun is not simply burning. It is a dynamic system of charged particles guided by magnetism. Its atmosphere is structured not just by heat, but by fields. These fields are invisible to human eyes, yet they control the rise of loops, the acceleration of particles, and the formation of storms. The Parker Solar Probe did not simply approach a hot star. It entered a magnetized plasma environment where the familiar rules of everyday air no longer apply. In that environment, magnetism becomes the framework. Plasma flows along it. Energy rides along it. Storms are born from it. Invisible lines shape visible light. And high above the surface in the corona, those invisible rails guide the very wind that sweeps across the solar system. By the time we reach the corona, the mystery feels clear. The outer atmosphere of the sun is far hotter than the surface below it. The question becomes simple to ask. Where does that extra heat come from? For decades, scientists have proposed several explanations. None of them are wild guesses. Each idea is grounded in plasma physics and magnetic behavior. They are more like suspects in a quiet investigation. One major suspect involves waves. In magnetized plasma, special waves can travel along magnetic field lines. These are called Alfvén waves. They are named after the physicist Hannes Alfvén, who helped develop the theory describing them. An Alfvén wave is not a sound wave. It is more like a ripple traveling along a stretched magnetic string. When plasma moves in the convective zone, it can disturb magnetic field lines. Those disturbances travel upward into the chromosphere and corona. As Alfvén waves move through the corona, they carry energy. If that energy is gradually absorbed by the surrounding plasma, it could raise the temperature. The idea is elegant. Energy rises from below in the form of waves. Those waves deposit their energy into the thin upper atmosphere. The challenge has always been measurement. How much energy do these waves carry? Do they lose enough of it in the corona to account for the extreme heat? The Parker Solar Probe has provided new data here. Its instruments have detected Alfvén waves much closer to the Sun than ever before. They observe strong wave activity in regions near the Alfvén critical surface. This supports the idea that wave-driven heating plays a role. But waves are not the only suspect. Another involves magnetic reconnection. Magnetic fields in the corona are constantly twisted and stretched by motion below. When field lines cross and reconnect, they release stored magnetic energy. This release can happen suddenly. Large reconnection events produce solar flares, but smaller ones may happen constantly. Some scientists propose that millions of tiny reconnection events occur throughout the corona. These are often called nanoflares. Each nanoflare would be small, too small to observe individually from far away, but together their combined energy could heat the corona to millions of degrees. It is like many small sparks adding up to a steady warmth. The Parker Solar Probe has measured magnetic fluctuations and small bursts of energy that may be linked to such events. The details are still being studied. Reconnection clearly occurs in the corona. The question is whether small-scale reconnection happens frequently enough to explain the full temperature rise. A third suspect involves turbulence. Plasma flowing outward from the Sun is not smooth. It contains large-scale motions and waves. These large motions can break into smaller motions. Energy cascades from big structures down to smaller and smaller scales. At very small scales, energy can turn into heat. This process is similar to how turbulence in water or air eventually dissipates energy as warmth. In plasma, turbulence interacts with magnetic fields. It can twist field lines at many scales. It can create small pockets where energy concentrates. The Parker Solar Probe has detected signs of turbulent cascades in the solar wind close to the Sun. It has measured fluctuations across different scales. These observations help determine how efficiently turbulence converts motion into heat. Each of these heating ideas has evidence. Waves clearly exist. Reconnection clearly occurs. Turbulence clearly shapes plasma motion. The challenge is determining how much each process contributes. It may not be a single answer. The corona may be heated by a combination of waves, reconnection, and turbulent cascades. The Sun is complex. Its atmosphere is layered and magnetized. Energy can move through it in multiple ways. The Parker Solar Probe did not arrive with a single theory to confirm. It arrived to measure. By entering the corona, it samples the region where heating must occur. It listens to waves directly. It detects magnetic shifts linked to reconnection. It observes turbulence as it unfolds. Each orbit adds new pieces of evidence. The mystery has not vanished, but it has narrowed. The suspects are clearer. The measurements are closer to the source. And as the spacecraft continues its journey, it moves through the very region where energy turns into heat. gathering clues before stepping even closer to the sun's core of unanswered questions. There is one term that quietly defines what it truly means to touch the sun. It is not a visible layer. It is not a glowing surface. It is a boundary made of motion. It is called the Alfvén critical surface. The name may sound complex at first, but the idea behind it can be understood slowly. The sun is constantly releasing material. This outward flow is called the solar wind. It is made of charged particles, mostly electrons and protons, streaming away from the sun in all directions. Near the sun, this flow is not free. The particles are still tightly guided by magnetic fields. They move along magnetic field lines. They spiral around them. They respond to magnetic tension. But as the solar wind travels farther outward, something changes. The flow accelerates. The particles gain speed. At some distance, the outward motion becomes strong enough that the magnetic grip begins to weaken. The Alfvén critical surface marks that turning point. It is defined by a balance of speeds. There are two speeds to understand. The first is the speed of the solar wind, the outward motion of particles. The second is the speed of Alfvén waves. Alfvén waves are ripples that travel along magnetic field lines in plasma. They carry energy and information. They allow disturbances in the magnetic field to move through space. Inside the Alfvén surface, these waves can travel both outward and back toward the sun. This means the sun and its surrounding plasma are still connected. If something disturbs the plasma, that disturbance can travel backward along magnetic lines and influence the sun's atmosphere. In this region, magnetism dominates motion. The sun still feels what happens there. But outside the Alfvén surface, the situation shifts. The solar wind flows faster than Alfvén waves can travel backward. Disturbances can no longer return. The plasma becomes free streaming. The sun loses direct magnetic communication with that outward flow. In simple terms, this is where the solar wind escapes. It is where the sun's atmosphere transitions into open space. There is no visible edge, no glowing ring, no solid shell. The boundary is defined entirely by physics. It is a change in who controls the motion, magnetism or flow. The term comes from Hannes Alfvén, a Swedish physicist who developed key theories about plasma behavior. His work helped establish magnetohydrodynamics, the field that studies how magnetic fields interact with conducting fluids like plasma. His ideas were once controversial. Today, they are foundational. For decades, scientists estimated where this boundary might lie. Models suggested somewhere between about 10 and 20 solar radii from the sun's center. One solar radius equals about 696,000 kilometers. That means the Alfvén surface was expected to be millions of kilometers above the visible surface. But until recently, no spacecraft had entered this region directly. We could only estimate its location. We could only infer its behavior from distant measurements. Then the Parker Solar Probe spiraled inward. As it approached the sun during its close passes, its instruments began detecting changes. Magnetic field measurements shifted. Wave behavior altered. Plasma conditions matched predictions for a magnetically dominated environment. On April 28, 2021, during its 8th close encounter, the spacecraft crossed the Alfvén critical surface. it entered a region where magnetic forces still controlled the plasma. For the first time, a human-made object was inside the Sun's extended atmosphere. NASA described it with a phrase that carried both drama and precision. Humanity had touched the Sun. The spacecraft did not reach the visible surface. It did something subtler. It crossed the boundary where the Sun's magnetic influence still holds sway. This boundary is not smooth. It is not perfectly round. Later data revealed that the Alfvén's surface has irregular shapes. It rises and falls. It forms spikes and valleys. Its location shifts with solar activity. During more active periods of the solar cycle, the boundary can expand outward. During quieter times, it may shrink inward. It behaves more like a breathing frontier than a rigid shell. Crossing this boundary matters deeply. It tells scientists where the solar wind truly begins its independent journey. It defines the region where heating mechanisms must operate. It marks the transition from magnetically controlled plasma to freely flowing wind. The Parker Solar Probe did not just approach heat. It crossed a physical threshold defined by speed and magnetism, a threshold once described only in equations, now measured directly, measured from within. The Alfvén critical surface is not something you can see. It is something you detect. It is the moment when the Sun's hold weakens, the point where energy begins to flow outward without returning, the place where the Sun lets go. There is a date that now stands quietly in the history of space exploration. April 28, 2021. On that day, during what engineers call Encounter 8, the Parker Solar Probe crossed a boundary no spacecraft had crossed before. The moment did not look dramatic from Earth. There was no explosion of light, no visible signal in the sky. The spacecraft was millions of kilometers away, moving in silence. But the instruments on board began detecting something different. The magnetic field patterns shifted. The character of the plasma changed. The data began to match what scientists expected to find inside the Sun's magnetically dominated atmosphere. The spacecraft had crossed the Alfvén critical surface. At that time, Parker was about 18.8 solar radii from the Sun center. That equals roughly 8.1 million miles from the Sun center. It was still far above the visible surface. Yet in physical terms, it had entered the Sun's extended atmosphere. The spacecraft did not cross the boundary only once. During Encounter 8, it moved in and out of the region several times. The Alfvén's surface was not smooth. It rose and dipped like uneven terrain. As the probe traveled along its orbit, it passed through valleys and spikes in that invisible border. Each crossing produced measurable signatures. Inside the boundary, magnetic fluctuations behaved differently. Alfvén waves showed patterns consistent with a magnetically dominated environment. Plasma density and particle speed shifted. Disturbances in the plasma could travel back toward the Sun. Outside the boundary, the solar wind flowed more freely. The outward motion dominated. The field lines were stretched outward, and the wind began behaving as a free streaming flow. The instruments on board recorded these transitions carefully. The field sensors detected changes in magnetic direction and wave speed. Particle instruments measured differences in velocity and density. Together, the measurements confirmed the spacecraft had crossed into the corona. This was not speculation. It was a shift in physical behavior recorded directly. The data was later analyzed and published in peer-reviewed studies. NASA summarized the achievement in language that was both poetic and precise. Humanity had touched the sun. The phrase captured attention, but the reality behind it was subtle. The spacecraft did not skim the photosphere. It did not descend into glowing plasma. It entered a region defined by physics rather than sight. The sun's outer atmosphere extends far beyond the visible surface. The Alfvén critical surface marks the point where magnetic influence begins to fade. Crossing it meant the probe had entered the region still magnetically connected to the sun. The event was a milestone, not because it was loud, but because it was direct. For decades, scientists estimated where this boundary might be. Now, it had been measured from inside. The spacecraft was traveling at extraordinary speed during this pass. At close approach, Parker moved at nearly 190 kilometers per second. That is about 687,000 kilometers per hour. At that speed, it became the fastest human-made object in history. Yet even at that velocity, the crossing was quiet. No physical barrier marked the moment. Only changes in magnetic and plasma behavior signaled the transition. It was like crossing an invisible shoreline in darkness. You cannot see the waterline, but the feel of the air changes. The current shifts. The motion beneath you becomes different. That is how scientists describe the crossing. A change in environment. A change in dominance. A shift from free wind to magnetic control. Encounter 8 was not the final crossing. Future orbits would carry the spacecraft even closer. With each Venus flyby, its orbit tightens. With each close approach, it spends more time inside the corona. But April 28, 2021, remains the first time a spacecraft entered that region. It marked the moment when a theoretical boundary became a measured place, when equations turned into direct experience, when a small machine, protected by carbon and careful engineering, moved into the sun's outer atmosphere. The crossing was not visible from Earth. It was recorded quietly in streams of data. Yet in that data, a long-standing line had been crossed. An invisible frontier had been entered. A shoreline without waves had been stepped across. And the sun, for the first time, had been touched from within its own atmosphere. It is tempting to imagine the sun's atmosphere as smooth, a glowing sphere surrounded by a neat, evenly spaced boundary. But the reality is more alive than that. When the Parker Solar Probe crossed the Alfvén critical surface in 2021, it did not pass through a single clean layer. It moved in, then out, then back in again. The boundary was not flat. It was uneven. It had spikes and valleys. During Encounter 8, the spacecraft crossed the Alfvén surface multiple times. Each crossing produced clear shifts in magnetic and particle data. Inside the boundary, magnetic forces dominated. Alfvén waves behaved as expected in a magnetically controlled region. Plasma disturbances could still travel back toward the sun. Outside the boundary, the solar wind flowed more freely. The outward speed exceeded the speed of Alfvén waves. The sun's magnetic influence weakened. The spacecraft moved through these transitions several times over a short span. This revealed something important. The Alfvén surface is not a perfect sphere. It is shaped by the sun's magnetic structures. Magnetic loops rise and twist above the photosphere. Some open outward into space. Some curve back down toward the surface. Where open field lines stretch outward, the boundary may extend farther. Where magnetic loops concentrate, the boundary may dip closer to the Sun. This creates an irregular surface. It expands and contracts. It rises and falls. It forms jagged edges in 3 dimensions. Scientists described it as having spikes and valleys. In some regions, the boundary reached farther into space. In others, it dipped inward. The Parker Solar Probe's path intersected these uneven structures as it traveled along its orbit. Earlier estimates had suggested that the Alfvén surface would lie somewhere between about 10 and 20 solar radii from the Sun's center. The 2021 crossing occurred at about 18.8 solar radii. This measurement helped confirm that the boundary exists within that predicted range. But the data also showed that its location is not fixed. The Sun operates on an approximately 11-year activity cycle. During solar maximum, magnetic activity increases. Sunspots become more frequent. Flares and coronal mass ejections occur more often. As activity rises, the structure of the corona becomes more complex. Magnetic field lines twist more intensely. The Alfvén surface can expand outward in some regions. During quieter periods, it may shrink inward. This means the boundary breathes. It shifts over time. It responds to the deeper motion inside the Sun. The fact that Parker crossed the boundary multiple times in one encounter demonstrates how dynamic the corona is. The Sun's outer atmosphere is not a calm, steady layer. It is structured by magnetism and motion. It changes shape over hours, days, and years. These measurements also refine solar models. Instead of assuming a smooth, spherical boundary, scientists now account for irregular geometry. They can simulate how spikes and valleys influence solar wind acceleration. They can examine how open and closed magnetic field lines shape the border. Understanding this irregular boundary improves space weather prediction. If the boundary shifts, it affects where and how solar wind streams form. It influences how disturbances propagate outward. It changes how energy escapes into interplanetary space. The Parker Solar Probe provided the first direct evidence of this uneven border. Before this, the Alfvén surface existed mainly in equations and simulations. Now it has measurable texture. It is not just a theoretical shell. It is a living frontier shaped by magnetic forces. The idea of a breathing atmosphere is fitting. The Sun's magnetic field expands and contracts. Loops rise and fall. Open channels widen and narrow. The boundary between magnetic control and free-flowing wind moves accordingly. When Parker passed through that region, it did not cross a still line. It crossed a shifting terrain, an invisible landscape with ridges and dips, a magnetically sculpted border. The Alfvén surface is not the edge of a solid star. It is the edge of influence, the place where the Sun's hold begins to weaken. And like the surface of an ocean stirred by currents below, it rises and falls with the energy of the star beneath it. A breathing atmosphere with jagged edges, marking the place where control becomes release. If the Parker Solar Probe had a main character, it would not be the instruments. It would not be the computers. It would be the shield. Without the shield, nothing else survives. Approaching the Sun is not simply about distance. It is about energy. At its closest approach, the spacecraft travels only a few million miles above the visible surface. The sunlight there is intense, nearly 500 times stronger than the sunlight that reaches Earth. That energy does not politely warm a spacecraft. It overwhelms it. It saturates it with radiation. It pushes temperatures high enough to melt metal. Standing between that heat and the delicate electronics behind it is the thermal protection system. This system is often simply called the heat shield. It is 8 feet in diameter. That is about 2.4 meters across. It looks like a wide, flat disc mounted at the front of the spacecraft. Its thickness is about 4.5 inches. That equals roughly 11.4 centimeters. For something protecting against the power of a star, it is surprisingly thin. The shield is made from carbon composite materials. 2 strong carbon plates form the outer layers. Between them is a lightweight carbon foam. That foam is about 97% air by volume. Air does not conduct heat efficiently. By trapping air inside its structure, the foam slows the transfer of heat from front to back. When the spacecraft is at its closest approach, the front of the shield can reach temperatures around 2,500 degrees Fahrenheit. That is about 1,370 degrees Celsius. Hot enough to soften many metals. Hot enough to destroy ordinary materials. Yet behind the shield, the spacecraft remains near room temperature, around 85 degrees Fahrenheit. The difference between front and back is dramatic. It is not magic. It is careful engineering. The front surface of the shield is coated in a white ceramic paint. This coating reflects as much sunlight as possible. Reflection reduces the amount of energy absorbed. What energy is absorbed must then move slowly through the foam core. By the time heat reaches the back of the shield, it has weakened significantly. The shield also creates shade. Most of the spacecraft hides entirely within its shadow. The instruments and electronics sit safely behind it, protected from direct sunlight. This means orientation is critical. The shield must always face the sun during close approaches. If the spacecraft were to tilt too far, even briefly, exposed components could overheat quickly. The heat shield does not work alone. It is part of a complete thermal strategy, but it is the most visible piece. It absorbs the full force of the sun's radiation, so the rest of the spacecraft does not have to. It is also surprisingly light. Engineers needed to balance protection with mass. A heavier shield would require more energy to launch. It would complicate the mission. So the design had to be strong, lightweight, and reliable. Carbon composite was chosen because it can withstand high temperatures without melting. Instead of melting, carbon tends to tolerate heat while maintaining structure. The foam interior reduces conduction. The white coating reflects energy. Together, these features create a barrier between fire and function. At nearly 700,000 kilometers per hour, during its fastest passes, the spacecraft moves through intense radiation. The shield stands steady at the front. It faces the star directly. It does not move aside. It does not bend away. It absorbs the energy so that sensitive instruments behind it can continue working. When we say humanity touched the sun, it was this shield that made that possible. A thin disk of carbon and air, a carefully measured thickness, a white surface reflecting light. It is easy to focus on the dramatic phrase. But behind that phrase is engineering discipline. The sun radiates power in all directions. The Parker Solar Probe meets that power with a circle of protection. A small disk standing between overwhelming heat and quiet measurement. Behind that disk, instruments listen. Behind that disk, data flows back to Earth. Behind that disk, a spacecraft survives where none had before. In open space, with no walls and no shelter, the shield creates its own shade, a patch of engineered shadow in front of a star. And in that narrow band of protection, the mission continues. The heat shield is the most visible protection on the Parker Solar Probe. But it is not the only protection. Survival near the sun is not achieved with one solution. It is a system. A balance of shade, reflection, cooling, and careful control. Behind the shield, the spacecraft must still manage heat that seeps inward. Electronics generate warmth of their own. Instruments must remain within safe temperature ranges. Even a small increase can affect measurements. To handle this, the spacecraft uses a closed-loop cooling system. The coolant is simple. It is water. Water flows through tubes connected to heat exchangers inside the spacecraft. As components warm up, heat transfers into the flowing liquid. That heated liquid then travels to radiators. The radiators are positioned carefully, so they remain in the shadow of the heat shield. In shadow, they can release heat safely into space. Space is cold. When radiators face away from the sun and remain shaded, they can dissipate heat effectively. The water then cycles back to collect more heat. This loop continues steadily during close passes. It is quiet. There are no fans, no open vents, just sealed tubing carrying liquid in a controlled circuit. The coolant system is designed to operate across extreme conditions. Between close encounters, the spacecraft travels farther from the sun. In those regions, temperatures drop sharply. The same system that prevents overheating must also prevent freezing. The coolant tank is equipped with heaters. These heaters keep the water from freezing when the spacecraft moves into colder space. This means the cooling system must adapt in two directions. It must protect against extreme heat near perihelion, and it must protect against cold between orbits. The solar panels require careful management as well. Solar panels provide electrical power, but near the sun, sunlight becomes overwhelming. If fully extended at closest approach, the panels would overheat quickly. To prevent this, the panels retract. As the spacecraft moves inward, only a small portion of each panel remains exposed. The rest slides back into the shadow of the heat shield. The exposed portion is just enough to generate the power needed for instruments and systems. Even this small exposed section faces intense sunlight, so it is cooled. Water from the same cooling loop runs through channels in the panel supports. This prevents the panel surfaces from exceeding safe limits. The panels are carefully angled and monitored. Like the shield, they must remain properly oriented. Too much exposure could damage them. Too little exposure would reduce power. The entire spacecraft operates within narrow margins. It must generate electricity. It must dissipate heat. It must remain aligned with the sun. All of these systems work together. The shield blocks most of the incoming radiation. The cooling loop removes internal heat. The radiators release that heat into shadowed space. The panels retract and extend as needed. This layered protection allows the instruments to remain near room temperature, even while the front of the shield reaches temperatures above 1,300 degrees Celsius. Without the cooling system, the shield alone would not be enough. Heat would slowly build up inside. Without retracting panels, power systems would fail. Without radiators, internal heat would accumulate. The mission depends on harmony between these systems. It is not one heroic component. It is coordination. The spacecraft carries its own small oasis of stability into an environment of intense brightness. A closed loop of water moves steadily through metal tubing. Radiators glow faintly in shadow. Panels slide inward and outward with precision. All while the sun pours energy outward without pause. The Parker Solar Probe survives not by resisting heat alone. It survives by managing it, by guiding it, by giving it a path to leave. In the brightness of the corona, the spacecraft maintains its own quiet climate, a small zone of controlled temperature in a region of extremes, an island of balance carried through a sea of light. And within that balance, the instruments continue listening, measuring, and recording as the mission unfolds. When the Parker Solar Probe approaches the Sun, it is alone, not emotionally alone, physically alone. At closest approach, radio signals between Earth and the spacecraft take about 8 minutes to travel one way. That means if something goes wrong, any instruction sent from Earth would arrive 16 minutes after the original problem began. Near the Sun, 16 minutes is far too long. Temperatures rise quickly. Radiation levels are intense. The spacecraft must protect itself without waiting for permission. This is where autonomy becomes essential. The Parker Solar Probe is designed to operate independently during its closest encounters. Engineers on Earth can plan the orbit. They can schedule instrument activity. They can upload instructions before the spacecraft dives inward. But during perihelion, the probe must guard its own survival. The most important rule is simple. Keep the heat shield pointed directly at the Sun. The shield must remain perfectly aligned. Even a small rotation could expose sensitive components to direct sunlight. To maintain alignment, the spacecraft uses a 3-axis stabilization system. 3-axis stabilization means the spacecraft controls its orientation in all directions. It can rotate around pitch, yaw, and roll. This allows it to hold the shield steady like a constant umbrella facing the Sun. Sensors continuously monitor the spacecraft's position. Sun sensors detect the intensity and direction of incoming light. Star trackers observe distant stars to confirm orientation. Inertial measurement units track small movements and rotations. If the spacecraft drifts out of alignment, onboard software responds immediately. Thrusters fire in short bursts to correct the angle. The system does not wait for Earth. It acts automatically. This automatic correction is not dramatic. It is subtle. Tiny adjustments made quietly in space. But those adjustments prevent overheating. They maintain the shadow that protects everything behind the shield. During closest approach, communication is limited. The spacecraft often pauses most transmissions to focus on data collection and thermal safety. It records information internally. It stores measurements for later transmission. The highest priority is survival. Only after the spacecraft moves farther from the Sun does it begin sending stored data back to Earth. Autonomy also applies to fault protection. The spacecraft contains software routines that monitor system health. If temperatures exceed limits, certain systems can power down. If electrical currents spike, protective steps are taken. If an anomaly occurs, the spacecraft enters a safe mode designed to maintain thermal protection and preserve core systems. Safe mode is not failure. It is controlled retreat. In safe mode, the spacecraft prioritizes keeping the shield pointed at the Sun and maintaining communication capability. Engineers can then analyze the situation once signals arrive. The environment near the Sun is not only hot, it is filled with radiation. High-energy particles can interfere with electronics. Memory systems must be shielded and protected. Software must account for potential glitches caused by energetic particles striking components. The spacecraft's design includes redundancy. Critical systems have backups. Key sensors are duplicated. If one component fails, another can take over. All of this allows the spacecraft to function in a region where human control is delayed. When Parker is closest to the Sun, it is the fastest human-made object ever built. It moves at nearly 190 kilometers per second. At that speed, it covers enormous distance in short time. There is no room for hesitation. The spacecraft must maintain precise orientation while traveling at extreme velocity through intense radiation. It does so quietly, without supervision in real time, without direct human steering. It maintains its shadow. It corrects its drift. It guards its own safety. There is something calm about that image. A machine traveling alone near a star. A machine designed to protect itself with logic and sensors. A machine that understands one simple rule: keep the shield facing the Sun. In that shadow, instruments continue listening. In that shadow, cooling systems circulate water. In that shadow, data accumulates. The Sun radiates without pause. Earth waits for signals that take minutes to arrive. And between them, a spacecraft holds its position with quiet precision, guarding its own shade, maintaining its own balance, flying calmly when Earth is 8 minutes away. Getting close to the Sun is not as simple as aiming at it. From Earth, everything in the solar system is already moving sideways. Our planet orbits the Sun at about 30 kilometers per second. Any spacecraft launched from Earth inherits that sideways speed. Even if you point it straight toward the Sun, it still carries that sideways motion. It keeps orbiting. To truly fall inward, you must remove orbital energy. And removing orbital energy is difficult. It requires strategy. The Parker Solar Probe does not rush toward the Sun. It works its way inward step by step. It uses Venus as a staircase downward. When a spacecraft flies past a planet, gravity can reshape its path. This is called a gravity assist. Most people think of gravity assists as speed boosts. They can be, but they can also slow a spacecraft down relative to the Sun. The effect depends on the geometry. When Parker flies past Venus, it gives up a small amount of orbital energy. Venus steals a little of the spacecraft's momentum. The spacecraft's path tightens. Its orbit becomes smaller. Its closest point to the Sun moves inward. This does not happen in one dramatic swing. it happens gradually. The mission design included 7 planned Venus flybys between 2018 and 2024. Each flyby lowered the perihelion. Perihelion is the closest point in an orbit around the Sun. After launch in August 2018, Parker's initial orbits were cautious. Its closest passes were far from the Sun compared to where it would eventually go. Engineers observed how the shield performed. They monitored the cooling systems. They checked instrument behavior. Only after those early tests did the orbit begin tightening significantly. Each time Parker returned to Venus, it approached from a carefully calculated angle. The spacecraft did not collide with the planet. It skimmed past at high speed. Venus bent its trajectory. The result was a narrower ellipse around the Sun. Picture a stretched oval. One end of the oval comes closer to the Sun. The other end reaches outward. After each Venus encounter, the inward end moves closer. The orbit repeats, again and again. This repetition is the key. The spacecraft does not dive once and stay there. It loops back out. Then it returns. Then it dives deeper. The path is like tracing a flower petal around the Sun. Each petal grows smaller. Each loop tightens. Eventually, the perihelion reached about 0.046 astronomical units. An astronomical unit is the average distance between Earth and the Sun. 0.046 astronomical units equals roughly 6.2 million kilometers, about 9.9 solar radii. That is extraordinarily close. For comparison, Mercury orbits at about 0.39 astronomical units. The earlier Helios 2 spacecraft reached about 0.29 astronomical units. That was the previous record. Helios 2 reached speeds around 252,000 kilometers per hour. Parker would go far beyond that. But it did not achieve this with an enormous rocket push. It achieved it by trading energy with Venus. Each gravity assist acts like stepping down a stair. You cannot step down all the stairs at once. You move one level at a time. Venus becomes part of the mission, a silent partner shaping the orbit. The timing of each flyby must be exact. If Parker arrives too early or too late, the geometry changes. The angle of approach determines how much orbital energy is exchanged. Mission planners calculate these trajectories years in advance. The math is precise. Small errors can compound over time. But when done correctly, gravity assists allow incredible changes in orbit without burning huge amounts of fuel. This is the elegance of orbital mechanics. The spacecraft is not fighting the solar system. It is cooperating with it, using planetary motion to reshape its own path. With each orbit, the Sun appears larger from the spacecraft's perspective. The radiation grows stronger. The environment becomes harsher. Yet the descent remains controlled, deliberate, measured. The Parker Solar Probe's path is not a straight plunge. It is a tightening spiral, a pattern of elongated ellipses, each one drawing closer. Venus bends the path. The Sun pulls the spacecraft inward, then Venus bends it again. Over the years between 2018 and 2024, the mission steadily reduced the distance. Each flyby was like stepping down one more stair toward the star. The process required patience. It required trust in celestial mechanics. it required accepting that closeness must be earned gradually. Instead of one dramatic dive, the spacecraft walked inward, orbit by orbit, flyby by flyby, using gravity as a quiet tool, using Venus as a staircase. And with each step down, the Parker Solar Probe entered deeper into a region no spacecraft had entered before. There is a kind of speed that feels abstract. You can read the number, you can repeat it, but your mind struggles to picture it. The Parker Solar Probe travels at that kind of speed. At its closest approach to the Sun, the spacecraft reaches a perihelion distance of about 0.046 astronomical units. An astronomical unit is the average distance from Earth to the Sun. 0.046 of that distance equals roughly 6.2 million kilometers, about 3.8 million miles, or about 9.9 solar radii from the Sun center. That distance alone is remarkable, but the speed is what truly feels unreal. At perihelion, the spacecraft reaches about 687,000 kilometers per hour. That equals around 430,000 miles per hour. In scientific terms, it travels at roughly 190 kilometers per second. Every second, it moves nearly 200 kilometers. In the time it takes to blink, it covers a distance greater than the width of many cities. To understand how extraordinary that is, comparison helps. Earth orbits the Sun at about 107,000 kilometers per hour. Mercury, the fastest planet in our solar system, orbits at around 171,000 kilometers per hour. The Parker Solar Probe moves far faster than either, more than 6 times faster than Earth, 4 times faster than Mercury. Even compared to previous spacecraft, the difference is dramatic. In the 1970s, the Helios 2 spacecraft set a speed record. It reached about 252,000 kilometers per hour at a distance of 0.29 astronomical units from the Sun. That record stood for decades. Parker surpassed it easily, and then surpassed it again. With each tightened orbit, its speed increased further. Why does it move so fast? The answer lies in gravity. The closer an object moves to the Sun, the faster it must travel to remain in orbit. Gravity pulls strongly inward. Orbital speed increases to balance that pull. This is why Mercury moves faster than Earth, and why Parker, moving far closer than Mercury, becomes the fastest object ever built by humans. Speed near the Sun is not optional, it is required. Without that velocity, the spacecraft would fall inward uncontrollably. Instead, it sweeps past the Sun in a tight arc, then climbs outward again along its elliptical path. During perihelion, the spacecraft is moving at its maximum speed. As it moves farther from the Sun, gravity slows it slightly, but at closest approach, the numbers peak. Nearly 190 kilometers per second. It is difficult to imagine such motion because there is no air rushing past, no sound, no vibration felt by human senses. The spacecraft moves through near vacuum. It travels silently, yet it covers distance at astonishing rates. In just 1 minute at top speed, Parker can travel more than 11,000 kilometers. That is farther than the distance across many countries. The spacecraft becomes a tiny spark whipping around a giant fire, a small object tracing a tight arc around a star. And despite that speed, it remains precisely oriented. Its shield faces the Sun, its instruments collect data. Its systems adjust automatically. The combination of extreme proximity and extreme velocity defines this mission. The record is not only about breaking numbers. It reflects the physics of orbital motion. As gravity pulls inward, speed rises. As speed rises, energy shifts. As energy shifts, the spacecraft can swing back outward and prepare for the next pass. Each orbit is a balance between gravity and motion. The faster it moves, the more carefully it must maintain alignment. The faster it travels, the shorter the time spent at closest approach. The Sun's pull accelerates it. Venus's gravity reshapes the orbit, and the result is the fastest human-made object in history. There are rockets that launch violently from Earth. There are probes that travel far into deep space. But no other spacecraft has moved this quickly relative to the Sun. The Parker Solar Probe reaches speeds that once belonged only to equations. Numbers that once lived in textbooks, now embodied by a machine moving quietly through the corona. A spark moving too fast to hear. A blur in silence, whipping around a star that has burned for billions of years. When the Parker Solar Probe moves through the corona, it does not see the Sun the way we do. It does not rely on color or brightness alone. Instead, it senses invisible forces. It listens to magnetic tension. It feels streams of charged particles flowing past it. Two major instrument systems make this possible, working together like paired sensors placed directly inside the Sun's atmosphere. The first system measures electric and magnetic fields. This instrument suite is called fields. Rather than taking photographs, it detects the invisible structure of space around the spacecraft. Magnetic fields thread through the Sun's outer layers, twisting and stretching as plasma moves. These fields can store enormous amounts of energy. Fields measures how strong those magnetic fields are and tracks how they change from moment to moment. It records tiny fluctuations as well as larger shifts that signal dynamic events. In addition to magnetic fields, the instrument measures electric fields. Electric and magnetic fields together carry energy through plasma. From these measurements, scientists calculate something called Poynting flux, which describes how much electromagnetic energy is moving through a region of space. That energy flow is critical to understanding how the corona stays so hot. Fields also detects radio emissions produced by solar activity. During flares and other energetic events, the Sun releases bursts of radio waves. By capturing these signals close to their source, the spacecraft gains insight into what is happening in real time. One of the most important things Fields measures is wave motion in plasma. Alfvén waves, named after physicist Hannes Alfvén, travel along magnetic field lines and can transport energy outward. By observing these waves near the Sun, scientists can determine how much energy is being carried upward into the corona. If those waves break down into turbulence, that energy may turn into heat. Fields acts like a sensitive fingertip pressed into an invisible current, detecting shifts in magnetism that no human eye could ever see. The second major system measures the particles themselves. While Fields studies the invisible forces shaping plasma, the particle instruments examine the plasma directly. They measure electrons, protons, and helium nuclei, often called alpha particles. These charged particles make up the solar wind. The instruments determine how many particles are present, how fast they are moving, and how hot they are. Some of the particle sensors face directly toward the sun. These are known as solar probe cups. They extend slightly beyond the heat shield's protective shadow, so they can directly sample the wind flowing outward. They are built to withstand intense heat and radiation, operating in conditions far more extreme than most spacecraft instruments ever encounter. Other sensors observe particles from the sides, allowing scientists to measure how particles move in different directions. By sampling from multiple angles, the spacecraft builds a three-dimensional picture of the solar wind's behavior. Together, the field instruments and the particle instruments reveal how energy moves from magnetic structures into particle motion. If magnetic fluctuations grow stronger, particle speeds may increase. If waves dissipate energy into turbulence, particle temperatures may rise. By comparing the two datasets, scientists can link invisible magnetic forces to measurable physical outcomes. Near the sun, the solar wind is still forming. It has not yet reached its full speed. It has not fully broken free from magnetic control. By sampling the wind at this early stage, the Parker Solar Probe provides information that cannot be gathered from farther away. The field instruments feel the invisible rails guiding plasma. The particle instruments measure the flow riding along those rails. There is no sound in space, no rushing wind to hear. Yet the spacecraft senses motion all around it. It detects magnetic tension and counts charged particles streaming past. It measures waves traveling through lines of force. Like invisible fingertips extended into plasma, these instruments allow the probe to feel the sun from within its own atmosphere. So far, the Parker Solar Probe has been feeling the sun. It has measured invisible magnetic fields and counted charged particles streaming past at tremendous speeds. Now we shift from touch to sight. The next two instrument systems allow the spacecraft to detect high-energy radiation and to image the solar atmosphere from inside it. Together, they add depth to the picture, helping scientists connect invisible forces to visible structures. The first of these systems measures the most energetic particles near the sun. It detects particles ranging from about 10,000 electron volts up to 100 million electron volts. These energies are far higher than those measured in the ordinary solar wind. Such energetic particles are often produced during solar flares, when magnetic field lines snap and reconnect, releasing enormous amounts of energy. They can also be accelerated by shock waves created when coronal mass ejections push violently through the corona. When a flare erupts, part of the released energy heats the surrounding plasma. Another portion accelerates particles to extreme speeds. By measuring these high-energy particles close to their source, the spacecraft helps scientists determine where and how that acceleration happens. Do particles gain energy directly at flare sites, along expanding shock fronts, or through turbulence in the surrounding plasma? Observations from near the sun help narrow down those possibilities. These measurements are important not only for theory, but also for safety. Energetic particles can damage spacecraft electronics. They pose radiation risks to astronauts traveling beyond Earth's protective magnetic field. By understanding how and where these particles are produced, researchers can improve space weather forecasts and better anticipate dangerous radiation events. The instrument does not see these particles, in the visual sense. Instead, it detects their impacts and measures their energy levels. From those readings, scientists reconstruct the physical processes that created them. The final major instrument system on board provides something different. It captures images. This imaging system consists of 2 telescopes that look outward from the spacecraft's position. It observes sunlight scattered by free electrons in plasma. When sunlight interacts with charged particles in the corona and solar wind, a small portion of that light is scattered. By detecting this scattered light, the instrument reveals structures that would otherwise remain invisible. Through this technique, the spacecraft captures images of streamers stretching outward from the sun. It observes jets of plasma erupting into space. It records coronal mass ejections as they expand and interact with surrounding plasma. Because the spacecraft travels so close to the sun, these images provide a perspective never achieved before. Instead of observing the corona from millions of kilometers away, the spacecraft images structures from within the environment itself. It is like watching a storm while standing inside the clouds, rather than viewing it from a distant satellite. These images provide crucial context. When magnetic fluctuations are detected by the field instruments and particle speeds change in response, the imaging system can reveal visible structures associated with those changes. If a coronal mass ejection passes nearby, the imaging system can show its shape and motion, while other instruments measure how magnetic fields and particle flows react. This layered approach allows scientists to connect cause and effect more clearly than ever before. By combining high-energy particle measurements with wide-angle imaging, the spacecraft bridges theory and observation. It links energetic bursts to flares and shock waves. It matches local turbulence to larger structures unfolding across the corona. The spacecraft does not simply pass through the sun's outer atmosphere. It senses invisible forces, detects energetic bursts, and watches storms develop from inside the solar environment. Together, these final 2 instrument systems transform the mission from a close flyby into a deep exploration. The probe is not only feeling the sun's invisible structure, it is watching solar weather unfold around it. From within the corona, it observes storms in motion and measures the particles they accelerate. In doing so, it turns the sun from a distant glowing disk into a dynamic, measurable world. For decades, the sun was something we studied from far away. We measured its brightness. We tracked its surface storms. We built equations to explain the strange heat above it. But every explanation came from a distance. The Parker Solar Probe changed that. It did not land on the sun, and it did not need to. It entered the corona. It crossed the boundary where the solar wind is still shaped by magnetism. It took measurements from inside the sun's outer atmosphere for the first time in history. That crossing confirmed something profound. The corona is not a simple shell. It is structured. It is uneven. It has spikes and valleys. The probe moved in and out of that boundary, showing that the sun's atmosphere does not end in a smooth line. It breathes. It shifts. It changes with solar activity. What once existed only in theory is now supported by direct data. We have learned that switchbacks, those sharp bends in magnetic field lines, are common close to the sun. We have seen turbulence cascade through plasma, carrying energy from large magnetic motions down to smaller scales where it can become heat. We have measured how the solar wind accelerates while still under magnetic control. We have watched coronal mass ejections from inside the environment where they begin. The sun has become less abstract, less distant, more measurable. And this knowledge matters. Solar storms are not just beautiful displays of light. They can disturb satellites. They can interfere with communications. They can affect power grids on Earth. The Carrington event of 1859 showed how powerful a geomagnetic storm can be. Today, our world depends on technology that is far more sensitive. By understanding how energy builds and moves through the corona, scientists improve space weather forecasting. Each close pass adds detail to models that help protect modern infrastructure. Yet many questions remain open. The corona still reaches temperatures of millions of degrees, while the surface below it is much cooler. The balance between wave heating, magnetic reconnection, and turbulence continues to be studied. The exact mechanisms that dominate under different conditions are still being refined. The mission has brought us closer to answers, but it has not closed the book. And perhaps the most remarkable part of this story is that it is not finished. The Parker Solar Probe is still active. It is still looping around the sun in tight, blazing arcs. It is still diving into the corona again and again. With each orbit, it gathers more data from deeper within the solar atmosphere. It remains the fastest human-made object ever built, moving at nearly 190 kilometers per second at closest approach. And with each pass, it pushes our understanding a little further inward. A small machine moves through intense heat and silent vacuum, protected by a shield no wider than a small room. Behind that shield, instruments continue their quiet work. They measure fields, they count particles, they image storms, they send their data back across millions of kilometers to Earth. The sun is the star that lights our world. It has burned for billions of years. It still holds mysteries in its heat and magnetism. But for the first time, we are not only watching it from afar. We are inside its atmosphere, listening. Close enough to measure, close enough to touch, and still humble before what remains to be understood.